There is a speed limit in our universe. It's not just a good idea, it's the law. The law of physics, to be precise. That ultimate speed is the speed of light. Nothing we know of, nothing with mass, can travel at this incredible speed, let alone faster. It's a mind-boggling velocity, fast enough to circle the Earth more than 7 times in a single second. This cosmic speed limit is one of the most fundamental pillars of modern physics, a cornerstone of Albert Einstein's theory of relativity. This universal rule seems absolute and unbreakable. As an object with mass gets faster and faster, it requires more and more energy to accelerate it further. Pushing something to the speed of light would require an infinite amount of energy, which is simply impossible. The universe has drawn a line in the sand, and the speed of light is that line. But what if there was a loophole? What if there were particles that existed on the other side of this light-speed barrier? Imagine particles that are born already traveling faster than light. They gave these hypothetical particles a name that sounds as fast as they are supposed to be: tachyons. The word itself comes from the Greek word tachys, meaning swift or fast. The name was first proposed in the 1960s by the physicist Gerald Feinberg. He was exploring some of the strange mathematical possibilities that pop out of Einstein's equations. He imagined a particle that always travels faster than light. Unlike the matter we are familiar with, which scientists call bradyons, or slow particles, tachyons could never slow down to the speed of light. A tachyon would have some very peculiar properties. One of the most bizarre is its relationship with energy. As a tachyon loses energy, it would speed up, accelerating towards infinite speed. Another strange property is that tachyons would have what we call imaginary mass. In physics, when we see imaginary numbers pop up, it often signals that something is physically impossible. In quantum field theory, imaginary mass is a sign that the state you are describing is not stable. It would instantly condense, releasing huge amounts of energy. The existence of tachyons would shatter one of the most sacred principles of physics: causality. The simple idea that a cause must always happen before its effect. If we could send a signal using tachyons, we could, in theory, send a message into the past. You could receive a reply to a question you haven't asked yet. This leads to the famous grandfather paradox. What if you sent a message back in time that prevented your own birth? The universe cannot both contain you and not contain you at the same time. From a tachyon's point of view, the universe would be a chaotic jumble of cause and effect. A shattered glass might reassemble itself on a table, which is then knocked over. For a tachyon moving away from you, you would see 2 images of it at once. You would see one image as it is now, and a ghostly image from its past, appearing to move towards you. Scientists reasoned that if charged tachyons existed, they should produce Cherenkov radiation not just in water, but in the vacuum of space itself, a unique trail of light we could detect. Starting in the late 1960s, physicists designed experiments specifically to look for this signature. They used sensitive detectors to scan the skies for unexplained flashes of light. Despite the ingenuity and dedication of the scientists involved, every single one of these searches came up empty-handed. There were no mysterious flashes of light, no particles behaving in the strange way a tachyon should. Another clever way to search for tachyons relied on conservation of momentum and energy. If the numbers don't add up in particle collisions, it's a sign that something invisible is carrying energy away. This missing energy technique was precisely how the neutrino, a ghostly particle that barely interacts with matter, was first postulated and later discovered. Scientists sifted through enormous amounts of data from particle decay experiments, looking for events where the missing momentum and energy fit the profile of a faster-than-light particle. Once again, the search proved fruitless. While physicists have struggled to find any trace of tachyons in the real world, science fiction writers have embraced them with open arms. They've become the ultimate plot device. Need to send a message faster than light to warn the fleet of an impending attack? Use a tachyon communicator. Need to travel back in time? Build a tachyon-powered time machine. Without some form of FTL travel or communication, the grand scale of a space opera would be impossible. Tachyons provide a convenient and science-sounding way to bypass this inconvenient truth. Perhaps the most famous early popularizer was Ursula K. Le Guin. In her Hainish cycle, she imagined the Ansible, which used tachyons to allow instantaneous communication across any distance. In Star Trek, Tachyons are frequently detected as a sign of temporal anomalies, cloaking devices, or beings from other dimensions. The word has become reliable technobabble for scriptwriters. They've even been used to explain superpowers. Dr. Manhattan from Watchmen experiences past, present, and future all at once, a state directly inspired by tachyonic properties. The story of the tachyon is a perfect illustration of how science actually works. Theoretical physicists imagined what a tachyon would be like. Then experimentalists designed clever tests to hunt for them. The failure to find tachyons is not a failure of science. It is a success. Every experiment that came back empty helped us draw the map of reality more accurately. Ultimately, the Tachyon saga teaches us about humility. It reminds us that our theories are just models, our best attempts to describe a universe far stranger than we can imagine. Our fascination with tachyons tells us more about ourselves than about physics. It reflects our deepest desires as a species, the dream of exploration, discovery, and connection. The dream of faster-than-light travel is about breaking the chains that bind us to our single, lonely planet and reaching out to the stars. A young person who watches a starship jump to faster than light might be inspired to learn more about real physics. They might even become the scientist who one day makes a breakthrough we can currently only dream of. Tachyons may not be real, but they will remain a ghost that haunts the beautiful mathematics of physics, a reminder of what might be possible within the laws of nature. While tachyons may be off the table, the quest for faster-than-light travel continues. Concepts like wormholes and warp drives are being seriously studied at the extreme edge of our understanding. Whether we ever achieve this dream or not, the act of striving for it is what defines us. It pushes our science, fuels our imagination, and inspires us to look up at the night sky not as a limit, but as an invitation. The journey continues, and the universe is waiting.